mixed together. They're not all the same. And in fact, we can even go a step further and look at the same spot, same crater wall, with our high-resolution camera, and we'll see that in the next slide. And when we do that, we see that there's even finer detail that's exposed. Remember, this is the one where the pixel size is now less than a yard across, more like a foot or so, as opposed to the 18 yards or so that we saw in the previous ones. And yet, even in its color, even though it's only a 3-color image, we see correlations in which the light tone units are descriptive of a certain kind of aqueous mineral on the surface. And we can use that spatial relationship to say a couple of things. One, things have been deposited with time. So there's been a change in the environment at the surface over time. And that's reflected in the physical record, not only the shape of the crater and its erosion, but also in the composition of what its walls are made of. That has been exposed by this crater that blasted in. Whether or not the layers themselves represent a continuous stratigraphic sequence in time, or whether there's a missing piece to the history, is something that we're still exploring. What we're trying to do is to look at the rest of the planet to see if we see a similar kind of sequence in those minerals. And we'll take a look at that more in another area here. So let's go to the next slide. And this is what a cross-section through that particular crater wall might look like. The reddish areas are more altered by the action of water. That is, the minerals that are there have seen water come through. Could be groundwater, could have been surface water at the time they were exposed at the surface. And they have changed. And that has left the record of the presence and duration of that water. Other areas are not as heavily altered. And that suggests that there are different times in Mars history, perhaps even episodic times of wetter or drier events, transitioning from what was once an ancient wetter climate to the drier climate of today. Going to the next slide, there's a diversity of these kinds of areas. We've identified at least 8 compositional types, if you will, units of the surface of Mars. And what we're trying to do is to classify the surface as to where these are exposed, how extensive are they in their coverage of the planet. Are we looking at local events? Are we looking at regional events? Or are we even looking at a global stratum that was put down at one time in Mars history? From A to B to C to D, what you're doing is you're coming forward in time, A being the most ancient of the terrains that we see there. And yet we see exposures when we look into that terrain. It's covered today by volcanic materials that came later in Mars history. But there are exposures, either where ravines or canyons cut through them, or where craters have excavated the material and exposed the strata that are there. Each of the colored areas in these scenes, again, these are false colors indicating the mineral deposits and different types of mineral deposits, are indicating a sequence of things that happened over time. And generally speaking, the environments changed in their nature. They were more neutral, that is, not as acidic as you'll see in some of the later environments, which we're going to get to the next slide. That's important because as things get more acidic there, the likelihood of preserving certain kinds of things on the surface, carbon-bearing materials, including if life ever developed on the planet, our question is, where should we go to look for the information that said it was there at one time? Where would that biological record be preserved? That's better done in the more neutral kinds of minerals that are formed on the planet. Those are better than the acidic ones, which may have released, eaten up the carbonates and other things that might have been there, and taken that carbon and put it back into the atmosphere for a short time at least. Let's go to the next set, which is shown here. And what you see here, the blue, by the way, are the sand dunes. And Mars, you see dunes in almost all the low areas. You saw them in Victoria Crater back when we were looking at the rover site there. You see them here in many of these sites. And in the lower right, what you see are a series of dunes. They're in a vast sea of dunes around the north polar cap of Mars. And what we're seeing there is a type of mineral, that gypsum, that is identified, and we can locate that it's in the dunes and not in the bedrock that the dunes are sitting on. So that means that that's an erosion product, probably out of the layered terrains that are presently composing the polar cap on Mars. So here's a remnant, here's something that has happened and been eroded away in more recent geologic time, a younger deposit, but telling us there are still active processes on the planet, and there are still, in this later period of Mars geology, there is still some alteration of materials that was going on at the surface of Mars. All right, let's go to the next one. We're going to zoom in on parts of the Valles Marineris systems. To call these canyons is really not representative of the scale of these features and such. You should think of them like the great rifts on the Earth, like the rift in Africa. For those in California, think of the Owens Valley or other similar kinds of things, tectonically produced. That's actually a question. Were they formed first or were they eroded in place? And we'll get to that question here. This is a section of that, and we're going to zoom in on a different section of the canyon system. Next slide, please. And what you see here is a perspective that we can take, the computer can give to us as if we were standing on the surface. It's constructed from a stereo image pair that lets us put ourselves anywhere in this scene. And the scales here, there is no vertical exaggeration to this perspective. So what you're looking at is the way the scene would look if you were standing on the surface. Some of the knobs and hills that are out there are a couple of football fields in length. They're up over 100 feet or so high in some cases. And you'll notice that they have a dark cap rock on many of those hills. This is like being in the American Southwest and looking at the mesas and the buttes that you'll see there, where there's a resistant cap rock that has presented erosion of the underlying materials. So the question is what is the nature of this? Is this the original material, and so that the rifts and the canyons were actually cut down into it by erosion? Or did those rifts form tectonically, were later filled with materials, which, after all, suggest a lot of activity on the planet, including possible aqueous activity, including in these deposits, filled the rift afterwards and then have been eroded away since by subsequent water flow or by wind erosion. By looking at the faults, the cracks in the ground, and looking at the stress patterns along the edges of these deposits, we can judge that, no, it's the latter, not the former. That is, the rifts formed first, they were filled with materials, water came and went in these deposits, altered the materials that were there, and left the scene that we see today as it's being eroded away by the winds. We're going to fly into this in a video that will take the three-dimensional scene, so let's go to the next videos. And you'll get a feel for looking at this landscape. Again, there's no vertical exaggeration in these. So you're looking at what would sort of look like if you flew over Utah, looking at the Canyonlands or the Capitol Reef National Monument. And this landscape is one that has been eroded heavily. It's been fractured. It's some places the ground is moved and defaulted into the, or faulted into the scarps that you see. A very fantastic landscape, not exposed everywhere, but exposed here because these deposits have been eroded. And looking at the multiple layers that are exposed here, obviously, you can see we have a lot of work to do to try to get the history that is preserved in that stratigraphic record, that sequence of the layers telling us about Mars. Okay. So let's go to the next one. What we're going to do here is fly into a different place on Mars where there's been a different water action. This is Mojave Crater, a very large impact crater on the planet, one of the younger ones, however. And what you see are terraces and such where water has ponded on those terraces and flowed down. As you go over the rim, note that the channels go right up to the peak of the rim. That means that this couldn't be springs in the ground that where water has emerged onto the surface and flowed down the slope. This is rainfall that must have come from the sky because it's eroded everything right up to the crest of that crater rim. Now, whether that was a persistent rainfall as part of a climate in which rainfall was a regular thing, or whether it was something that was actually associated with the impact itself. Think of a giant meteor crashing into ground, particularly if it's ice-laden. All of that ice is going to be volatilized back into the atmosphere, and for a time, there's a tremendous overburden that will condense out and come back down as rain. Whether you can do all that erosion in that one single event is one of the things that we're trying to look at with the detail that we have. And for the first time, we have the detail to see that. On the next slide, here's the footprints of some of our instruments, and it gives you another sense of the scale of what we're able to do. The ones outlined in white, the sort of butterfly pattern, that's our imaging spectrometer. As it flies